There's a famous building in London called the Walkie-Talkie Building. It's shaped like a walkie-talkie, so it's called like that. And it's famous for melting things and putting things on fire. One of the stories says that there was a driver parked his car on the road in front of this building somewhere. And when he came back, he saw that the rear view mirror, the side mirror was melted. Another story says that there was a doormat again somewhere in front of the front of this building. And again, and it was found that it caught fire suddenly. And so many such incidences happen, and we're pretty sure it's caused by this. So somehow this is setting things on fire in front of it. So why does it do that? Well, we will be able to answer this question satisfactorily at the end of this video. Now, to answer this question, we need to talk about curved mirrors. And one of these curved mirrors are called concave mirrors. And that's what we'll do in this video. We'll explore what these concave mirrors do, we'll understand their properties, and finally we'll be able to answer our question. Before we start with concave mirrors, let's start with what we already know, what we might already know. We might have some experience with flat mirrors, plane mirrors. So imagine we have a plane mirror where the right hand side is the reflecting side. And let's say we incident some rays of light. Let's incident a parallel ray of light so that it's easy to analyze. What do you think will happen to these rays after reflection? Well, you may have already studied the rules of reflection. The angle of incidence always equals the angle of reflection. So to use this, we always draw a normal. So let's draw the normal. We draw a normal. A normal is just a perpendicular that we draw at the point where the incident ray is hitting the mirror. So we draw the normal, draw the perpendicular, and then the angle between the incident ray and the normal becomes the incident angle, or the angle of incidence, and that is 0 over here, everywhere. And therefore, from the rules of reflection, even the angle of reflection must be 0, because angle of incidence always equals angle of reflection, which means the reflected ray will just retrace its path. And so if you could see the reflected rays, it would be somewhat like this. It would have retraced its path. Okay, so this is something that we might have seen before. Now, the important thing to note over here is that the incident rays were parallel, and after reflection, even the reflected rays were parallel to each other. That is something to note over here. Okay, now let's see in contrast what happens if we have a concave mirror. So let's look at a concave mirror. A concave mirror is a curved mirror, and if you look at it carefully, you see it's the inner part that is reflecting. Since this inner part is sort of like a cave, we call this mirror as a concave mirror. You can think of a spoon, and the part of the spoon that you use, the stuff that you put inside the spoon, the inner part, that is the concave part of it. All right, so this is a concave mirror. And so the question we want to think about is, what's going to happen if we incident some rays of light on a concave mirror? Again, let's incident parallel rays of light. I like to draw parallel rays because they're easy to analyze. You can draw any rays actually, but parallel rays are pretty easy to analyze, so let's draw them. And so the question now is, what will happen to these rays of light after reflection? Well, we don't have any experience with curved mirrors so far, but we know what happens to flat mirrors. So I'll tell you what I like to do. What we can do is we can, wherever the rays of light are hitting the mirror, we'll zoom in over there. We'll take a very tiny patch of that mirror and we'll assume it's flat. Okay, so let me just show you what I mean. So what I'll do is, so if I want to know what happens over here, I'm just going to zoom in as much as possible, as much as this software allows me to. All right, so here it is. And I'm going to assume this to be a flat part of the mirror. So let's say this is flat like this. Okay, let's zoom back out. And we can do the same thing everywhere else. If I look at this over here, this part over here, I can pretty much assume it's a flat mirror, isn't it? This looks pretty much flat to us. Any curve you take, and if you zoom enough on it, if you take a very small patch of a curve, you can approximate to be flat. We do the same thing with Earth also, right? Earth is a curve, but when you look at a small part of it, it looks flat to us. And the reason we are doing that is because if you think in terms of flat mirrors, we know what to do. We can draw normals, and then we can figure out where the reflected light will go. So let me go back. Here it is. So we have 3 tiny flat mirrors, and we can now draw normals. I should have drawn normals earlier. Let me go back and draw now. Let's draw a normal over here. So a normal is perpendicular to this. So let's draw perpendicular to this. It's not exact, but you can sort of see now. Can you visualize what the angle of incidence is? The angle of incidence is over here, which means the reflected ray, so this is the incident ray, so the reflected ray must go somewhat like this. All right, so let's do over here. Let's see what happens. Over here, again, if you draw a normal, normal is going to look like this. The incident ray and the normal are aligned. That means the angle of incidence is 0. So the reflected ray will just go back because the angle of reflection will also be 0. And similarly, we can do the same thing at the top. And I want you to pause the video now and try to visualize this yourself. Can you visualize this and think where the reflected ray will go? Just pause and see. All right, let's do this. Again, we'll draw a normal. Normal must be perpendicular to this surface. So if you drop a normal, this is what the normal looks like. And here is the angle of incidence. And so we can see the reflected ray to go somewhat like this. Again, the angle of reflection must be the same as angle of incidence. So if we zoom back out, so let's zoom out. What do you see? Well, notice that after reflection, the rays of light are no longer parallel to each other. But if we extend these rays of light, and I have not drawn this properly, but if I did draw it properly, you would see, let me just rub this a little bit. Okay, if you had drawn this properly, you would see that these 3 rays of light are actually going to meet at one single point. All right, and when the rays of light meet at a point, we say that they are converging at a single point. And after converging, the rays of light will just continue on their path, which I've not shown. But what's important is that after reflection, the rays of light are no longer parallel, but they're converging to a single point. And the beauty of this shape is that if you get this shape right, we'll talk more about this shape in the future videos, but if you get this shape right, then we will see that even if you draw more parallel rays of light, and if you continue the same thing, you will find out if you again zoom in and you draw normals, and if you draw it carefully, not like the way I've drawn it, but if you draw it carefully, you will see even these reflected rays will converge to that same point. And if we draw even more rays of light, regardless of how many parallel rays of light you draw, you will see all the rays of light will meet up at that single point. And that point where the rays of light are being focused, being concentrated, we give a name to that point. We call that as focus. Such a nice name. It's called as the focus of this particular mirror. All right, so now we can go back to that initial question and see if we can answer it. So if you look at this front face of this building, you can sort of see through it, right? That's because it's made of glass. And what's important to understand is glass can reflect light. Not all of light, not like a mirror, it can reflect some of it, but since we're dealing with such a giant piece of glass, even some small amount of light that it reflects becomes significant, okay? And so basically this is acting like some kind of a reflector. And more importantly, look at the shape of the building. It's not flat. If you look at it carefully, you see it is curved inwards. Look at this curve. Look at this curve. It's inwards. So it's acting like a concave mirror. And that's why when you have sunlight, okay, so let me just draw. When sunlight hits that particular glass face or the front face of that building, the rays of light from the sun are pretty parallel, and we'll talk a little bit about that. Don't worry, we'll talk about that. But anyways, after reflection, just like what happens here, all these rays get focused at a single point. And of course, it turns out that this point of focus really depends on, the location of this focus really depends on at what angle these rays of light are coming and all of that. But let's not worry about that. What's important is that it does get focused at a single point. And at some particular part of the day, that focal point lies on the road. And so if you park anything at that location, then all the sunlight is being concentrated. I mean, all the light that is being hitting this particular glass piece, most of it's getting concentrated at one single point, producing a very high intensity spot over here. And that is enough, producing a lot of temperature, and increases the temperature, producing a lot of heat, and that's why things are getting melted. And what's mind-boggling for me is that, notice that this is pretty flat. It's not all that curved, but it is curved. Even that small curvature is enough to focus that sunlight and cause enough problems. That's pretty amazing. Okay, before I wind up, we just want to show you one thing. Why did I say that the rays of light from the sun are parallel to each other? That's all I want to show you. So let me quickly go to another screen. Let's say we have a tiny bulb, which is giving out light in all the directions. And what we'll do is we'll dim this light. Let's dim that light. And now let's keep a mirror in front of this. Let's say it's a concave mirror itself. And we'll only concentrate on the rays of light that are hitting or that are being collected by the mirror. Now notice when the mirror is close to the bulb right now, the rays of light that are hitting the mirror are pretty much trying to go away from each other. You can pretty much see that. However, if we take that same mirror and we keep it far away from the bulb, now notice if you were to look at these two rays of light and you forget about everything else, you just concentrate on those two rays of light which are hitting the mirror. Yeah, if you only look at these two rays, don't they look pretty much parallel to each other? Even though these rays are actually originating from that same point. So long story short, what's happening is when we keep our mirror close to the bulb or close to the source, the rays of light don't look parallel. But when you keep it far away, and what do we mean by far away? Far away means the distance between the mirror and the source must be much larger compared to the size of the mirror. That's the whole idea. I hope you agree that if the size of the mirror was large, then a lot of rays would hit, and then again, the rays will not be parallel. But if the size of the mirror is much smaller than the distance, then the rays of light are parallel. And if this was the sun, then Earth would be extremely tiny. It would be pretty much a dot over here. And so since the size of the Earth is much smaller than the distance between the Earth and the sun or the source, we can pretty much very nicely assume that the rays of light from the sun is parallel when it comes and hits the Earth. All right, so now let's go back. So to quickly summarize, what we learned over here is that when you take a mirror and you curve it in such a way that the inside part is reflecting, we call that as a concave mirror. And what do concave mirrors do? Well, we saw logically that they can focus a parallel beam of light to a single point, and it concentrates that light, and we call that point as the focus. And that's why the walkie-talkie tower, which acts like a concave mirror, ends up burning things when you keep things at the focus of that particular building.